It's one of the gas industry's riskiest construction projects ever. The longest subsea pipeline in the world. Giant ships lay 100,000 pipes linking Norway to Britain. Space-age robots trench an underwater moonscape beyond the reach of human hands. A project on this scale has never been done before. Will this survive the brutal North Sea? "120 kilometers off the coast of Norway is one of the North Sea's largest underwater gas fields. It's called Ormen Lange. At 40 kilometers long and 10 kilometers wide, and containing over 300 billion cubic meters of gas, it's simply massive. But it's locked in an icy tomb 3,000 meters below the sea surface, so deep and so remote that it's considered beyond the reach of man and machine. That is, until the engineers at Norsk Hydro, the Norwegian energy company, decide it's just too tempting to ignore. Because there is enough gas to supply 20% of Great Britain's gas needs for 40 years. The engineers know that in Britain there's an expanding market for natural gas. The coal they have traditionally been using to power their economy is no longer sustainable. The Brits are increasingly using foreign gas to power the turbines that create the electricity for their homes and factories, and they need more of it. So the engineers have come up with a plan. It will take 10 years and cost $10 billion. First, they'll drill the Ormen Lange gas deposit, transport the gas 120 kilometers to one of Norway's largest processing plants at Nyhamna, then send the processed gas to the UK down the Langeled pipeline, a staggering 1,200 kilometers. But to build the world's longest subsea pipeline this far and this deep requires overcoming some not-so-simple problems. They're drilling nearly 2,000 meters through the seabed to tap the gas field. And they'll do this with a rig built right on the sea floor. The real fun begins with this, the Storegga slide. The pipeline that brings the gas out of the field and delivers it to the plant has to scale this 300-meter underwater cliff face. And the seafloor terrain is too rough to lay pipe on, so that means trenching this monster. The gas itself is a dangerous mixture of debris and frozen water that could blow a processing plant apart. So they're adapting the system to handle the Ormen Lange gas. The plant is big enough to turn through 70 million cubic meters of the stuff each day. To handle this mega job, they've amassed some of the largest industrial ships in the world, each designed to tackle a specific phase of the deep sea construction. Out here, in the harsh North Sea, humans are confined to the topside world. Beneath the waves, the brawny work is done by these, underwater remote-operated vehicles, or ROVs. They're a fantastic new breed of machines, and are so technologically advanced, they're the stuff of science fiction. It's a monumental challenge, but with a pile of gas industry money behind them, the engineers can dare to dream. But are these guys going too far? Can they make this dream come true? Or is this going to be an engineer's nightmare? First, they searched the world for a gas well platform, which would work in these torturous seas. Existing designs fall short. The weather here is too stormy. The water too deep. Then, they suggest a revolutionary solution. If they can't bring the gas up to a rig, why not take the rig to the gas? Inside this warehouse in Tonsberg, on the coast of Norway, the key piece of solving that engineering challenge is being built. It's a daring move. The engineers are combining the function of a surface platform with a seabed drill guide. It's called a template, and it's an underwater gas platform that guides the drills through to the gas field and controls the well flow. Conventional gas platforms are sea surface structures manned by an army of workers. In this case, the platform is dropped onto the seabed, clear of the wild North Sea weather. A drill ship then docks to it, and from above guides the drills through to the gas field. When the drilling is finished and the gas is flowing, the drill ship departs, leaving the template to control the wells. 4 of these monsters will be mounted on the seabed. Through them, a total of 24 wells can siphon over 70 million cubic meters a day from the gas field. The template will then direct and control the gas flow to a shore-based plant. The entire unit operating by remote control from a manned center 120 kilometers away. Richard Benyon is a subsea engineer.
The main thing that you've got, the difficulty that you've got, is it's dark, it's the devil of a job to put it in the first place. You've got to get this equipment onto the floor. It's highly valued, highly priced piece of equipment, and then you've got to put it together with robots, and you've got to make sure it doesn't leak. Apart from that, it's easy.
The stakes are huge. Engineers are building it to withstand pressures that would crush a normal submarine. And it has to operate flawlessly for over 40 years in a harsh saltwater environment. Once it leaves this warehouse and is lowered to the sea floor, there's no going back. It's going to be committed to the seabed forever. This 1,000-ton monster can't float on its own, so the structure is loaded onto a seagoing barge for transport to the drop site. With all the planning and building behind them, it's the weather that will determine if this mission is a success or failure. It's a 4-day journey to the drop site, and they've planned it to coincide with summer. It's the season of the calmest seas, which doesn't mean much here in the North Atlantic. They rendezvous with the world's largest crane ship, the Thielf, a super crane that does heavy lifts at sea. The 2 cranes mounted on board can lift over 14,000 metric tons. That's about 80 747 jumbo jets. The barge and Thielf wait for a weather window before lift operations begin. The contract to install the subsea components is worth $21 million. With so much at stake, they practice back on shore. The crane and ROV operators rehearse the drop. This is a 3D virtual underwater world, like the one they'll be working in. With weather, depth, and weight going against them, they practice. Now it's time for the real thing. Lines are connected. The record-breaking sea drop begins. This is their only chance. If they miss and it settles on the seabed in the wrong place, they'll have to build another one and set the project back by a year. Computer-controlled thrusters hold the crane ship over the drop site. As it goes below the surface, the underwater ROVs are put into action to take over as the eyes on the operation. They feed video back to the control room. The engineers scan the rig for problems as the pressure increases. From 1,000 meters below, the ROV feeds video back to the crane operator, who adjusts the orientation. They have to keep the ball bearing as close as possible to the center of the bullseye. He keeps the drop going, even when it's meters away from the sea floor. He's committed. There's no stopping it now. It's down, and it's so heavy, the legs on the base sink 8 meters into the seabed. But they won't know if they landed on the right spot until they check the coordinates. The reading shows it's within 40 centimeters of their target, close enough to be considered a perfect drop, accomplished from 1,000 meters above on a rolling sea. Now that the template has been successfully placed, the next step is to tap the gas field. It takes 2 years to drill the first 8 wells, and they must have them ready to go before the pipeline can be connected. A specialized drilling ship, the West Navigator, is moved into position over the top of the gas field. The Ormen Lange gas wells will be the largest deep-water wells drilled in the world. They drill the field with a powered drill head operated from the ship. Once assembled, the pipe is lowered through the bottom of the ship and the 1,000 meters to the template. From here, the drill head moves another 2,000 meters through the seabed to the gas deposit. And then it snakes its way through the gas pockets. Every step of the way is monitored and recorded in a virtual database, which keeps expanding and is used by the engineers and surveyors to plot the next drilling spot. Back on land, the team can enter the cave, an amazing 3D undersea world. By virtually passing over the seabeds and the gas find, they can locate the most promising parts of the deposit. Jens Grimsgaard can plot the drill's movement from the cave.
With a joystick, I could also fly in this world by just using it, this tip here, and using my movements of my hand to steer myself through this reservoir.
During the drilling, data collected by the drill is sent back in real time to this database, which is constantly being updated. The computer generates the images, which puts the team right in the gas deposit. They pinpoint spots from 10 kilometers away with astonishing accuracy.
That would be compared to that your dentist would be in the 10th floor, and you would be situated in the first floor, and he's going to fill out one of your tooths back there. We're getting extremely good results by doing this.
The template gets its power from the land through a 125-kilometer control cable called an umbilical. This cable carries huge amounts of electricity, enough to power 20,000 homes. Combined in this umbilical cable are tubes carrying hydraulic fluid, fiber optics, and electrical cables. The welds on these tubes have to be as strong as the welds on the pipeline. This is the power and control connection to the template. Without this, the template will be just 1,000 tons of useless metal at the bottom of the North Atlantic. But how do they deal with a cable that is a staggering 125 kilometers long? The cable is built in a factory right on the dock. As the cable is made, it is fed onto a giant spool on the deck of the Scandi Neptune. Once the 120 kilometers of continuous cable is spooled up, it will head out to the Ormen Lange gas field to connect the control room to the 4 underwater templates. But now, they have to prepare the seabed. The bottom of the ocean under the North Sea is a treacherous place. And, as you're about to discover, the engineers building the world's longest underwater pipeline are facing a mountain of trouble. 8,000 years ago, 2 pieces of Norway, each about the size of the island of Tobago, slid into the sea, causing a mega tsunami. The landslide, known in Norwegian as the Storega, created a huge shelf in the ocean's topography. The Ormen Lange gas field is on the edge of the Storega, locked inside the huge depression left behind by the slide. This underwater disaster created a mountainous seabed with peaks that rise between 25 to 55 meters. But the biggest concern for Hydro is how to get the pipeline up the Storega slide face, a whopping 300 meters. That's nearly as tall as the Empire State Building. Underwater surveys reveal a rugged and fractured seabed, but the unstable sediments have long ago disappeared. The rock is more than stable enough, and it would take a new ice age to dismantle it again. But the study has made them more aware of the seabed and the pathway they will need to clear for the pipeline that will connect the underwater gas rig to the land. First, they must build a 3D model of the sea floor and find the easiest route. What they have created is a virtual reality program. With this model, the engineers are able to plot the best pipeline route. The fisheries in the North Sea is a huge industry, and Hydro has to make sure the pipeline will not damage the reefs where the fish feed and the fishing boats work. But the concern is not just about the environmental impact at sea, but also on shore, where one of the largest gas plants in Norway is being built. The land connection they have chosen is the small island of Gossen and the tiny community of Nyhamna. The destiny of this quiet community will be forever altered now that it's been chosen as the landing area and processing plant for the Ormen Lange gas project. What was once a remote corner of Norway is being transformed into the bustling industrial center of the Ormen Lange gas project. Here, the raw gas from the Ormen Lange gas field will be converted into usable fuel. But to do that, over 2 million cubic meters of rock is being carved from the island, and over 30,000 tons of steel brought in. Almost overnight, what was once a small village has become the busiest construction site in Norway. Over 2,200 workers are on the job site each day to keep this mega gas plant rising from the rocky coastline. There's a canteen to feed 1,000 people in a city. Each night, the workers retire to the hotel, which will provide 1 million guest nights over the course of the project. But it will be removed when the processing plant is up and running. Three-dimensional models of the plant have been built, and the engineers walk through it in virtual reality before and during construction. Every bolt, I-beam of steel, is pre-visualized. Because of the volatile gas, the specifications have to be executed perfectly. But the plant has been built for efficiency. The raw gas travels through the pipes and is converted into usable fuel in a mere 10 minutes. That's a blink of an eye in this business. Then it will be ready for delivery to the UK. The gas processing units are delivered to the island by ship. Cranes offload the components onto this massive flatbed transport. This remote-controlled monster has 48 independent axles and 96 wheels. It expertly shuttles the thousands of components needed to build the plant. Here on land, the workers have a close working relationship with the job site. But offshore, the workers hand in their wrenches for what else? Joysticks. Offshore, the underwater work is done with remote-operated vehicles, or ROVs, from pipe laying to heavy lifting. And that requires a lot of different ROVs and people who can operate them. In this warehouse is a simulation tank built just for offshore personnel to train on ROVs. It's driving school for robot jockeys. Here, they simulate projects that will take place offshore. It takes special tactile skills to maneuver a crane arm from 1,000 meters away. Multiple cameras allow the operators to see the action. After the intense training with the ROVs, they're sent offshore, where the stakes are high and it's no longer a game. There are no second chances. This is the Pipeline End Termination Unit, or PLET, a big machine for one simple task. It connects the underwater template, or gas well, to the Ormen Lange pipeline. But it's never that simple. At 35 meters long and 30 meters wide, this 350-ton device is being lowered the 1,000 meters to the sea floor. Now that the PLET is on the sea floor, they assemble its components. Called modules, these components make the crucial connection between the template and the pipeline that feeds gas to Nyhamna. All the connections at this depth are made with ROVs. But they can't do any of this work without first testing the systems. Thomas Berndt is the Subsea manager.
We are testing and testing and testing here, and when we leave this hole, we are 100% sure that this connection will be tight when we come offshore. There won't be any leakage. A leakage offshore at 850 meters with large volumes of gas is a disaster, which we have to avoid.
They practice lowering the modules and testing the connections, which will be handling 70 million cubic meters of gas each day. They're training with an exact replica of the one that's on the sea floor. It's a large investment, but money well spent. Surrounding the connection module is a steel cage that protects it from stray objects that could drop off the drill ships and fishing trawlers. When the gas exits the field, the steel pipe expands. A little bit of expansion is okay. But the reason they're going to this much trouble is they expect the Ormen Lange pipeline to expand along its entire length by as much as 1 meter. and that's enough to rip it apart. So they've solved this by using a connector that slides back and forth on rails. It absorbs the pipe's movement and keeps the gas flowing. Meanwhile, the engineers are tackling the Storegga slide and trying to get the umbilical cord, or control cable, run from the template to the control center, 120 kilometers away. But to do this, they have to find a way through the rough and tumble terrain left in the wake of the slide. The solution is to build an underwater excavator, agile and strong enough to handle the job. It's a daunting prospect. That is, until they built the Spider. The machine that inspired this one was originally built for the Swiss forest industry. And like its Swiss cousin, the Spider moves along using powered tracks and articulated legs. Its mission is to excavate 6 trenches at water depths up to 1,000 meters. The biggest of them is a 4-meter wide by 4-meter deep monster trench, big enough to drive a truck through. One Spider is outfitted with a powerful shovel. It's strong enough to cast aside a 3-ton boulder. Instead of a shovel, the other Spider has a suction nozzle. Powerful water jets break up the sea bottom, and the nozzle sucks it up and fires the mud to the side. All the while, the Spiders will contend with slopes up to 35 degrees. There are sensors on all movable parts, connected through an umbilical from a support vessel, which floats above and monitors its progress. The umbilical carries power and control cables and lets operators manipulate the 6-meter-long Spider to within 10 centimeters of accuracy, 10 centimeters from 1,000 meters above. It's an unprecedented mobilization of such complicated and agile robots. In all, these 2 champion diggers managed to excavate 3,500 cubic meters of soil, creating a safe path for the gas pipeline. The Langeland, which runs 1,200 kilometers from Norway to the UK, is the largest subsea pipeline in the world. This job requires 1/3 of the world's combined pipeline production capacity. That's over 1 million tons of steel. The value of the pipeline contracts is an unimaginable $700 million. Langeland uses pipes over 1 meter in diameter, and each single piece of pipe has to be able to stand the enormous pressure on the sea floor for the next 40 years. The pipes are each 12 meters long and weigh 10 tons. Another 10 tons of concrete and metal is added to give them enough weight to stay on the ocean floor. A total of 100,000 steel pipes are needed to span Norway to the UK. That includes over 1 million tons of concrete and 25,000 tons of steel reinforcing. Robert Payne is the man responsible for the integrity of the pipeline as it's being assembled.
Each joint of pipe weighs about 20 tons, about 10 tons of steel, 10 tons of concrete. It's concrete and it's got inside of it a wire mesh foundation to help it stick together. There's so much volume inside of it, whenever it gets on seabed and it gets light of air, it wants to float, so the concrete keeps it situated on seabed.
Each of the 100,000 pipes is numbered as it comes out of the plant, destined for a specific location in the line. As the team is trenching on the steep Storegga slide, the rest of the route from the top of the slide to the shore is being prepared. This is the Island Frontier. It's a state-of-the-art trenching ship that combines 2 types of trenching methods into one powerful machine. They survey the flat areas where they think they can bury the pipe by scraping a trench through the sandy bottom. What they discover is not a pretty picture. The sandy bottom is actually clay, and the clay is hardened like concrete. A new digger is required to cut a channel up to 7 meters wide and 5 meters deep. The margin for error is only 50 centimeters on the width and a crucial 10 centimeters on the depth. The clay cutter hybrid, the only one in the world, is lowered to the seabed. The cutting tool uses its 24 water jets set at different angles to blast a trench through the clay. Suspended above is the 4-ton jet prop. The propeller draws in large volumes of the surrounding seawater, driving it at a high force towards the seabed, clearing debris from the trench. Transponders mounted on the sea floor relay a 3D picture of the operations to the control ship. And following along the entire operation, like a foreman on a job site, is an ROV that surveys the trench and confirms that it is dug to specifications. The battle of the clay is finally won. But when they start to lay the pipeline on the seabed, the problems really begin. The seabed under the North Atlantic is a tortuous and irregular landscape. There's over 1,000 kilometers of terrain like this along the pipeline route from Norway to England. It's so rugged that only small sections of these heavyweight pipes will actually make contact with the seabed. It's called free spanning, and they don't want it. It means the unsupported sections of pipe will sag, stress, and then break under their own weight. This would be an environmental catastrophe. They have to find some way of flattening out the pipeline route.
If you're not able to plane the seabed flat by moving the earth out of the way, you may have to fill in some holes with rock or other fill material.
They level the pipeline route by laying gravel down on the sea floor. This ship loads gravel into its cargo holds and delivers it to the area that needs leveling. It can carry over 9,700 tons of gravel at a time. Once at the job site, it uses a flexible fall pipe to place the gravel on the pipe pathway. Computers create a 3D model of the seabed and the path where the gravel needs to be placed. This method allows the crew to place the gravel precisely where they need it.
At these sort of water depths, you've got a problem because you haven't got that degree of control. I mean, whatever's doing the work down there is a huge distance away from the mothership, and they've got to still present a flat, smooth profile for the pipeline then to be laid upon. The other thing that has to be worried about is that you have to do that profiling as close as possible to the time that the pipeline is going to be laid, because Mother Nature tends to move things around again after you've left. And so you come back in a couple of weeks later and you find there's been a storm or whatever, and what you've taken so much care to flatten out has all of a sudden been moved around again. So you would lose the work that you've done before.
The pipe laying itself is a monstrous job. Once the pipe has been manufactured, it is placed onto the supply ships for delivery to the pipe-laying barge, the LB-200. The barge is huge, longer than 2 football fields. It's an enormous floating steel welding factory, which has to work with military precision. There are only 3 of this type of ship in the world, and Hydro is using 2 of them here.
Pipeline route has been surveyed before we ever came here. We have an ROV boat that stands by with us. It monitors the pipe as it touches seabed, and it's a predetermined route that we follow.
The barge has been used in the Gulf of Mexico, in the Mediterranean, and off the coast of West Africa. But this is its biggest and most historic assignment. Once the pipe-laying process starts, it cannot stop. Not for weather, for accidents, for anything. The pipeline is built as a continuous tube that is dropped from the ship to the seabed. If the ship halts for too long, the strain on the pipe could snap it. The barge moves along at 4 kilometers a day and needs a constant supply of pipe sections, which must be delivered in the order in which they are to be connected and laid down. It's 100,000 pieces of pipe laid down end to end in a predetermined pattern.
They get moved by crane 3 or 4 times and go through about 15 or 20 welding stations and coating stations.
The pipe sections are delivered to the assembly floor, deep inside the LB200. Here, the welders are divided into teams. Their job is to create sections of the pipe called double joints. These double joint sections are 24 meters long. There's a lot at stake. The pipes have to be put together so there's no chance of leakage, and the assembly line has to keep up a steady pace. The entire operation is monitored by engineers who have video cameras that put eyes on the process, both inside and outside the pipe.
It's incredible technology, but the fundamentals are very simple. The fundamental thoughts that go behind it, because it has to be so rugged and it has to work every time, first time, that the actual basic engineering is still fairly simple.
The next stage of the assembly line is to join this short section of pipe to the main pipeline. It's being fed out of the back end of the ship and onto the sea floor. It's a complex process that requires a lot of fine-tuning. This is no ordinary welding operation. The process involves a special welding machine with 8 heads per station. Passing through each of the welding stations in 7 minutes, the pipe is then checked by an ultrasound machine. If a flaw is detected, it has to be repaired immediately before moving to the next station. The process cannot be stopped. The connection has to be perfect, because this is the stage that welds them together forever. The assembly line is manned by industrial workers from over 30 countries. Shifts work around the clock to keep the assembly moving 24 hours a day. Each day, the teams have to assemble 3 to 4 kilometers of pipeline and drop it to the sea floor. After all the welding stations have linked the pipe, the final step of the operation is to seal the exposed metal. It is covered in a protective heat-shrunk plastic. Without this, the steel pipe would corrode in the seawater. Now, for the most critical step of the operation, offloading the pipe to the sea floor. The section where the pipes are joined is covered in foam to protect the welded joint during the drop. The decks are cleared and the pipe is now ready to be committed to the sea floor. A rubber tensioner grips the pipeline and holds it in place as it slides off the barge. As the pipe enters the ocean, it begins to sag and pressure is put on the entire pipeline, which is free hanging beneath the ship. Without exactly the right tension, the pipe could snap like a matchstick.
The pipe comes off the back of the barge in what's called a lazy S configuration. So it comes off the back of the barge and trails down to the seabed some distance behind. That S of unsupported pipe has to be kept from just buckling under its own weight. So to keep it under control, you've got to keep that under a huge tension to stop it from just collapsing under its own weight.
As the pipe is lowered, the barge moves forward 24 meters, not a meter more. With this well-oiled operation, the LB200 is able to lay over 100 kilometers of pipeline a month, as long as the pathway is clear. And clearing that pathway is a complicated process. In these particular sections of the pipeline route, they need a 2-meter deep trench. So they bring in the massive Saipem plow. This is the PL2. It's being used for trenching in shallower waters. It drops onto the seabed over the 1-meter diameter pipe, where its strong clamps pick it up. Then, as the surface ship pulls it forward, the plow cuts a trench 5 meters wide and 2 meters deep. To fill the trench, the BPL-2 follows behind with backfill to cover the pipe with a protective coating of sand. Early in the design phase, it was decided that they would bring the gas from the Ormen Lange field to the processing plant at Nyhamna, and then build another 1,200-kilometer pipeline to Britain. At the 600-kilometer mark, the line is broken and connected to the Sleipner riser platform. The Sleipner platform works as a hub, monitoring the 70 million cubic meters of gas flowing into the UK every day. But tying the pipeline into the platform creates a whole new set of engineering headaches. The underwater robots can line up the pipeline and the connecting pipes coming from the platform. A massive underwater crane moves them into position. But when they're matched up, there is no technology for replacing human beings in making the final connection. So the welders have to also become divers.
You ready to come down? Your hose good? Okay, he's ready to come down.
Thank you.
It's just that these welders are working on the sea floor. Like working on the moon, the divers move around in pressurized modules to the work site.
Do one lift on it and see if we can rotate it into its proper orientation with you guys. Oh. Hey, you're clear of that, Dearman?
Here, new edges have to be cut and beveled at each pipe end before the welding hub is lowered onto the joint to connect the two sections. The welding habitat is dropped to the ocean floor. It has to be maneuvered in place perfectly over the 1-meter diameter pipe. It clamps the pipe and then closes itself off. The habitat is pumped full of air, forcing the water out. Topside, the dive supervisor uses cameras to keep a close eye on them and watch for any danger. Once it's safe, the divers move from the module to the welding habitat. Within this habitat, the diver welders make the final, permanent connection. It's a tricky and dangerous procedure. The welders are confined to this small room, 72 meters down, and there's no escape if something goes wrong. As each weld is finished, the engineer checking by monitor on the ship above is able to inspect the work. This last weld completes the connection from Easington to the Sleipner gas platform, halfway from Norway. This is the first of many underwater welds that they'll need to make all the pipe connections to get the gas flowing. 600 kilometers of pipe still have to be completed. But a major goal has been achieved with this connection. Now that the pipe has been sealed and connected, it has to pass inspection before they commit it to the next 40 years of service. This is done with the pipeline internal gauges, also known as the PIG. It makes the epic journey through the entire pipeline, looking for weak spots and breaks. It also scrubs out the crud and salt water. Once in Easington, it emerges and the data is analyzed. The pipe passes inspection, and the team moves on to the next phase, which is getting the pipe onto land and into the gas plant at Nyhamna. But landfall is blocked by a surprise discovery. A mysterious shipwreck has been found 500 meters off the coast, lying in their path, and there is no way around it. The wreck is directly in the pipeline path. They have no choice but to halt work. They look for alternate routes, but the underwater terrain near the coast prevents the pipeline from going around or under it. They have to go through it. But before they can do that, they decide to study the wreck and recover as many of the artifacts as they can. The problem is that the shipwreck lies in over 200 meters of water, well beyond the reach of archaeological divers. Marek Jasinski is a professor of marine archaeology. His team is called in to research the wreck 500 meters from the harbor.
I don't think they were really happy when they found out that there was a shipwreck lying in the way.
It may have stopped the pipeline in its tracks, but for archaeologists, this is a fantastic opportunity to excavate and retrieve a piece of history. But it's hard enough doing a proper archaeological excavation in shallow water. At these depths, it's considered nearly impossible. So the team takes a page from the Ormen Lange engineers and utilizes a remote-operated vehicle that can do the archaeological recovery for them. These vehicles suddenly become a new generation of tools for the archaeologists. But the thrusters on the remote-operated vehicles stir up sediment and obscure the wreck site. So they create a way to put an ROV on the site and move it around without thrusters. The ROV docks to this steel frame, which covers a section of the wreck. Once attached to the frame, gears and pulleys control its movement with precision, and the archaeologists can get on with the job of unraveling the mystery of this shipwreck.
Our theory is that the ship was on its way to northern Russia, to Arkhangelsk, and that this ship was a part of the trade network between West Europe and northern Russia.
The find is amazing. They discover 18th century artifacts from Asia, the Mediterranean region, and all over Europe. Once the sand is cleared, fully intact wine bottles, plates, and coins are collected by the remote-operated vehicles.
Det blir spennende å se om det så vann eller saltvann inni.
Back in the lab, the find is being investigated. They may never know the name of the ship these artifacts are from, but it's an extraordinary opportunity to look into maritime history. An opportunity that may not have happened had the Ormen Lange pipeline not stumbled upon the wreck. But as problems are being solved in Norway, they're a long way from being solved in England. The coastal town of Easington is chosen as a landfall point for the pipeline. It's a convenient place to come ashore because it already has some gas industry infrastructure. But there's a huge snag here, which can potentially set the project back by decades. Each year, on the coast battered for millennia by the North Sea, the land around Easington gets smaller. Up to 2 meters of coastline disappear every 12 months. Over the 40-year life of the gas field, erosion could claim 80 meters of earth. To prevent exposure after erosion, the pipeline is routed through a 400-meter tunnel under the cliffs of the Easington coast, then brought up to the plant.
Yeah, I think you've got a system which is certainly as good as man can make it. I mean, if some set of forces came into play that we had no anticipation of, maybe we've got a different game on our hands, but we've got a fair understanding of the forces that that pipeline will be going through during its working life.
The erosion of the English coast is just one more problem faced by an engineering team already exhausting itself with designing solutions. Back in Nyhamna, they now have to deal with the raw gas that comes out of the Ormen Lange field. The problem is liquid slugs. What comes out of the gas field and through the pipeline is not pure gas. It contains large chunks of debris called slugs. The slugs move through the pipeline with such force that when they reach the treatment plant on land, they have the potential to explode like liquid bombs.
And they will come into the plant with quite high velocity, and there's a lot of mass in it. So if those came into the plant directly, it would probably destroy the plant.
The solution is to build a slug catcher, a labyrinth of pipes and filters. A 10,000-ton monster, it will meet the debris and stop it dead before it reaches the Nyhamna plant. Now, they have to contend with the millions of cubic meters of condensate. Every major gas producer ends up with condensate, a valuable stew of raw materials that can be turned into other types of energy. The problem is storing and then moving it. The solution here is to use huge underground caverns carved inside the Norwegian mountains. This mega-sized natural holding tank can be filled with 230,000 cubic meters of condensate. The engineers don't have to line the rock caverns with anything. Water pressure from the surrounding area forces the toxic sludge to stay confined within these walls. Every 4 days, the caverns are pumped dry, and freighters haul away more than 24,000 cubic meters of condensate. For this byproduct is also liquid gold, which can be turned into other types of fuel for the international marketplace. As the Nyhamna gas plant is completed, the final leg of pipe is being laid out to the Ormen Lange gas field, 120 kilometers offshore. A special ship is required to work in these dangerous waters close to the Norwegian coastline. It can maneuver in tight spots using dynamic positioning, moving meter by meter from shore to the Ormen Lange gas field. Out here near the Ormen Lange gas field, the Solitaire reaches the limit of its pipe-laying ability and can go no further. Its job comes to an end at the top of the Storegga slide. This is the most demanding part of the entire Ormen Lange project. The steep terrain left in the wake of the Storegga landslide requires a special pipe-laying ship. This is the S-7000. It's a former crane ship. It's been modified with a 130-meter tower on its stern deck. It's taller than a 33-story building. It's a floating factory. And it's so big, one can easily forget it's 100 kilometers offshore in the North Sea. 20,000 pipes are welded together in groups of 4. They lift the now 48-meter long pipe up into the 130-meter tower and then lower it onto the pipeline. Here, it is welded to the pipeline, and then the pipe is carefully eased through a series of tensioners within the tower and lowered vertically, straight off the ship. The entire operation takes a month to complete, making the final connection from the template to Nyhamna. With the final link made, the engineers have done what seemed impossible, built a super pipeline through some of the roughest underwater terrain on the planet. The question is, will this super pipeline deliver? What it has delivered is a gigantic leap in the technology of undersea engineering. The technological advances made here might well end up being used under the impenetrable Arctic gas fields. By the time this pipeline gets into full production, the huge army of divers, welders, engineers, and construction people will have already moved on to other projects, leaving behind them a super pipeline, hidden deep under the North Sea.